In this class, we will frequently encounter Hermitian matrices. So, a Hermitian matrix is one for which it's equal to its own conjugate transpose. So, note, by the way, we will use the notation H for the conjugate transpose. The Syed text that we'll sometimes refer to uses a different notation of a star. Both are common. I just looked at Wikipedia a few minutes ago, and one of the pages I looked at used the star for the Hermitian transpose or conjugate transpose of A. So if you see either of them, it usually means conjugate transpose. I'll try to be clear if we ever have to do something crazy like a simple conjugate. Okay, so for example, if we have A given here, 1j, where j is the imaginary number, 3 plus j, 1 plus j, then AH is going to flip the signs on all the j's and transpose the result. So this is sometimes referred to as a Hermitian transpose, or sometimes we'll even hear the term Hermitian, the Hermitian of A. That's a little bit confusing because technically, if A satisfies A equals AH, then we say the matrix is Hermitian. Well, Hermitian matrices have one really useful property. That is that they have only real eigenvalues. And we'll go ahead and show how this works right now. So, when I took linear algebra many years ago, I remember thinking that eigenvalues and eigenvectors were just some strange, useless trivia. It turns out that they form an integral part of the mathematics of this course. So here's a short review. If u is an eigenvector of A, then A times u is equal to lambda times u, where lambda is a scalar, and it's the eigenvalue associated with A and with u. In this case, we've got subscripts because A will have multiple eigenvectors and multiple potentially eigenvalues. Now you can use MATLAB to get you this information. In MATLAB, you just use the function eiga. It use help so you can see the actual format. It gives you two outputs, one being the eigenvalues and the other being the eigenvectors. In Python, you can use linalg.eig, or you can use scipy.linalg.sure. We'll talk about the sure decomposition in just a little bit. So, back to our original discussion of what happens with Hermitian matrices. Since A, actually I guess we need to do something else first. Let's do this. Since A is equal to, strike that, back up. Let's assume that ui is an eigenvector of A. If we multiply ui by some constant, in this case alpha, the constant can be pulled out of the front of that expression, so we get alpha times A times ui is equal to, since ui is an eigenvector, alpha times lambda I times ui. Well, then we can once again put the move the alpha around, and now we see that alpha times ui is also an eigenvector of A. And not only that, it has the very same eigenvalue, lambda I. Because of this, we can always choose our eigenvectors to be scaled so that they have a magnitude of 1. And by convention, we're going to do this. I'll mention it once or twice more just to make sure that's clear, but for the most part, just assume that that's what we're going to do. Okay, so now let's go back to look at this little statement up above, which is Hermitian matrices have only real eigenvalues. How could we prove this? Let's see. So, for a Hermitian matrix, let's multiply on the left by an eigenvector, the Hermitian transpose of an eigenvector. Then we have UIH times A times UI. Well, applying the properties of eigenvectors, A times UI becomes UI times lambda I, and since lambda is a scalar, we can move it around in the expression. And since we've just defined the L2 norm of UI to be 1, we get that this is equal to lambda I. Now let's do the same thing again, except this time we're going to take the conjugate transpose of the entire expression. When we do this, each element in that expression is conjugated and transposed, and the order is reversed. So because of the way we constructed it, everything looks the same except we've got the AH in the middle. Well, we constructed this problem such that A was Hermitian, therefore AH is equal to A, and we have the same expression we had above, which is that this is equal to lambda I. Therefore, lambda I is equal to lambda I Hermitian, which for scalar just means lambda I conjugate, and our eigenvectors, or rather our eigenvalues, are real. So, in summary, a matrix is Hermitian if it satisfies A is equal to A conjugate transpose, and Hermitian matrices have only real eigenvalues. We'll explore some more properties of Hermitian matrices in the next lecture.